Hello everyone, today we are going to read chapter Stereochemistry of Organic Compounds. This is chapter of Organic Chemistry of BSC Chemistry honours first year. So introduction of stereochemistry. One of the most important characteristics of organic compound is their ability to show isomerism. These are compounds which have the same molecular formula but different chemical and physical properties. It is of two types. First, structural isomerism. Second, stereoisomerism. So first we will do structural isomerism. Compounds having the same molecular formula but different structures, different arrangement of atoms within the molecules are called structural isomers, and the phenomenon is called structural isomerism. It is the following six types. Chain or nuclear isomerism. Compounds having the same molecular formula but different arrangement of carbon chain within the structure or molecule are called chain or nuclear isomers, and the phenomenon is called chain or nuclear isomerism. For example, the formula C4H10 represents two chain isomers. First, butane, N-butane. Second, 2-methylpropane, isobutane. Similarly, the formula C5H12 represents three chain isomers. First, pentane, N-pentane. Second, 2-methylbutane, isopentane. Third, 2,2-dimethylpropane, which is also known as neopentane. Likewise, the molecular formula of C6H14 represents 5 chain isomers. First, hexane, N-hexane. Second, 2-methylpentane, or also known as isohexane. Third, 3-methylpentane. And fourth, 2,2-dimethylbutane. And fifth, 2,3-dimethylbutane. Position isomerism. Compound which have the same structure of carbon chain but different only on the position of multiple double or triple bond or the functional group are called position isomers, and the phenomenon is called position isomerism. For example, but1-ene and but2-ene are position isomers like but1-ene and but2-ene. Likewise, but1-ine and but2-ine is position isomers, and buta-1,3-diene and buta-1,2-diene show position isomerism. Similarly, propane-1-ol and propane-2-ol are position isomers like N-propyl alcohol, propane-1-ol, and isopropyl alcohol is propane-2-ol. Third, function isomerism. Compounds having the same molecular formula but different functional group are called functional isomers, and the phenomenon is called functional isomerism. For example, the molecular formula of C2H6O represents the following two functional isomers: CH3CH2OH, ethanol, ethyl alcohol, and methoxymethane dimethyl ether. Similarly, the molecular formula C3H6O represents the following four functional isomers: propanone, which is acetone, propanol, which is propionaldehyde, and propane-2-ene-1-ol, which is allyl alcohol, and methoxyethene, which is methyl vinyl ether. Further examples of functional isomerism is carboxylic acid and esters. C2H4O2 represents ethanoic acid and methyl methanoate. B. Aldehyde and ketones. C3H6O represents propanone and propanol. C. Dienes and alkynes. C4H6 represent buta-1,3-diene and but1-ine or but2-ine. D. Allenes and alkynes. C4H6 represents buta-1,2-diene or N-alanine and but1-ine or but2-ine. E. Nitroalkanes and alkyl nitrites. C2H3NO2 represents nitroethane and ethyl nitrite. F. First, second and third amines. C3H9N represents propane-1-amine or first amine. N-methyl ethanamine is second amine, and N-dimethylmethanamine is third amine. G. Cyanides and isocyanide. C2H3N represents ethane nitrile and methyl isocyanide. H. Aromatic alcohols, phenols and ethers. CH-H8O represents benzyl alcohol, anisole, O-cresol, M-cresol, P-cresol, which can be said as orthocresol, metacresol and paracresol. It may, however, be noted that here orthocresol, metacresol, and paracresols are themselves position isomers. Metamerism. Compounds having the same molecular formula but different number of carbon atoms or alkyl groups or either side of functional groups, example O, S, NH and CO, are called metamers, and the phenomenon is called metamerism. Metamerism occurs among the members of same homologous family. Examples of metamerism: ethoxyethane or diethyl ether. Second, first methoxypropane methyl and propyl ether. Third, 2-methoxypropane isopropyl methyl ether. B. First, diethyl thioether. Second, methyl and propyl thioether. Third, isopropyl methyl thioether. C. Diethylamine. Second, methyl and propyl amine. Third, isopropyl methylamine. D. Pentane 3-on or diethyl ketone. Second, pentane 2-on or methyl and propyl ketone. Third, 3-methyl butane 2-on or isopropyl methyl ketone. It may be noted here that metamers may also be position isomers. For example, pentane 2-on and pentane 3-on may be regarded as a position isomer as well as metamers. Tautomerization. It arises due to 1,3 migration of a hydrogen atom from one polyvalent atom to the other within the same molecule. Isomers thus obtained which exist in dynamic equilibrium with each other are called tautomers, and the phenomenon is called tautomerism. These are several types of tautomerism, but keto-enol tautomerism is the most important in this type. Tautomerism, one form tautomers, contains the keto group, while the other contains the C double bond COH group. Two simplest examples of keto-enol tautomerization are acetaldehyde and acetone, from where acetaldehyde keto form converts into vinyl alcohols enolic form and negligible amount, and acetone keto form converts into prop-1-ene 2-ol enolic form to negligible amount. In simple aldehydes and ketone like acetaldehyde, acetone, etc., the amount of enolic form is negligible, small. However, if the enolic form is stabilized by intramolecular hydrogen bonding, such as in 1,3-dicarbonyl compounds, the amount of enolic form is much greater than in acetaldehyde or acetone. For example, in acetone acetic ester, the amount of enolic form is 7%. In same acetoacetic ester 1,3-dicarbonyl compound keto form is 93% and in enolic form it is 7%. Similarly, acetyl acetone 1,3-diketone also exhibit keto-enol tautomerism, but the amount of enolic is here much higher, 76%, than even in acetoacetic ester. This is due to the reason that keto group is a much better electron withdrawing group than the ester group. Acetyl acetone keto form is 24% and enolic form is 76%. Essential condition: for the aldehyde or ketone to exhibit keto-enol tautomerism, it is essential that it must have at least one alpha hydrogen atom. Thus, acetophenone, butane 2-on and propione aldehyde all contains alpha hydrogen atom and hence show keto-enol tautomerism. In contrast, benzaldehyde, benzophenone, etc. do not show keto-enol tautomerism because they do not have alpha hydrogen atoms. Similarly, nitro compounds also show tautomerism. Nitromethane, nitroform, aciform. Ring chain isomerism. Compound having the same molecular formula but possessing open chain and cyclic structure are called ring chain isomers, and the phenomenon is called ring chain isomerism. For example, C3H6 represents CH2 CH double bond CH2 propene and cyclopropane, which are ring chain isomers. B. C4H8 represents but1-ene and cyclobutane or methyl cyclopropane, which are ring chain isomers. Similarly, butene or 2-methylprop-1-ene are ring chain isomers. Cyclobutane and methyl cyclopropane C3H4 represents propyne and cyclopropene, which also ring chain isomers. Double bond equivalence. Double bond equivalence is also called index number or the index of hydrogen deficiency. The problems on structural isomerism and structural determination of organic molecules can be easily solved by the concept of double bond equivalent DBE, which implies the sum of double bond and ring present in the molecules. It is given by relation DBE equals to vol n nu minus 2 vol me by 2 plus 1, where n is the number of different kinds of atom present in molecules and U is the valency of each atom. For example, DBE for MF C3H6O equals to 3 bracket में 4 minus 2 plus 6 whole bracket 1 minus 2 plus 1 whole bracket 2 minus 2 whole divided by 2 plus 1 equals to 0 plus 1 equals to 1. This means the various structural isomers of C3H6O will contain either one double bond C or C double bond O, or one ring homocyclic or heterocyclic as discussed below under example 3.2. Likewise, 2DBE implies either two double bonds or one triple bonds or two rings or one double bond or one ring. Similarly, 4DBE implies either four double bonds or two triple bonds or two double bond plus one triple bond or three double bond plus one ring. For example, benzene ring or any other combination of rings, double and triple bonds. Example 3.1. Write all possible acyclic and acyclic structure of isomers of hydrocarbon with molecule mass 68. Solution step 1. To determine DBE, since the molecular weight of hydrocarbon is 68, therefore the maximum number of carbon atom 68 by 12 equals to 5 quotient and the hydrogen atom 8 the remainder, therefore molecular formula is C5H8. DBE for C5H8 equals to 5 whole bracket 4 minus 2 plus 8 whole bracket 1 minus 2 is divided upon 2 by whole plus 1 equals to 1 plus 1 equals to 2. Since DBE equals to 2, therefore C5H8 may contain a triple bond or two double bonds, one double bond and one ring or two rings. First, acyclic isomers. A. Acyclic isomers containing a triple bond are pent-1-ine, 3-methylbute-1-ine, pent-2-ine. B. Acyclic isomers containing two double bonds are penta-1,3-diene, 2-methylbuta-1,3-diene, penta-1,4-diene. All of this is for today. Thanks for watching.